recurrence relations, right? We've introduced them now. Specifically, we introduced them after integration by parts, right? Why did we do that? Why now? Why did it make sense together? Trust me, I do this all the time. Now, serious question. Integration by parts and then recurrence relations. Do you remember, like that was not just an accident, like we could do any order we like. What is it that linked integration by parts with recurrence relations? What was the point?
You needed by parts for recurrence relations.
Yeah, okay, sort of. Okay. Can we recite? What is the definition of integration by parts? The integral of u dv is equal to uv minus what? The integral of v du. Okay, now, the whole idea is that integration by parts works by introducing another integral, right? Now, therefore, if this integral looks anything like what you started with, right, and we noticed that there were some examples, like trig functions, like high powers of x and so on, where that occurred, you get an integral in terms of another integral that's similar to itself. And that's why we talked about this recurrence, okay? So let me see if I can tidy that up. Recurrence relations flow naturally out of integration by parts, okay? So therefore it can be tempting when you're sort of in this recurrence relations subtopic, right? It's tempting to use integration by parts for everything, right? It's that old saying, when you're holding a hammer, everything looks like a nail, okay? But it's not always a good idea to use integration by parts. Let's just do a very simple example just to illustrate it, okay? So have this down underneath where you've got your heading, okay? I will give you a simple integral, and I hope for your sake you can all see what it is and that you don't need integration by parts, right? If this is what we were asked to work with. Okay, and I actually gave a similar example to some of you last lesson, okay? We do not need to do this by parts, right? What would be a more sensible way to do this? I should use substitution, right? What should I introduce as my substitution? H equals 1, the inside function as it were, right? So this is really a clever use of reverse chain rule, but I'm just going to write it down. That gives you du on dx as 3x squared, because the 1 just vanishes, right? And now you can substitute it. It's very simple, right? If I call this I is going to be equal to the 3x squared and the dx. They become our du, our change of variable. And what you're left with is this. No big deal. Now, just for the sake of illustration, let's consider what would happen if you gave this a go, but thought, aha, look, it's a product. This times this. Integration by parts, baby. Okay, let's see what happens. What would you do? Okay, what would you choose as u, and what would you choose as dv? There's an obvious choice. Think about it. You want dv to be easy to integrate, don't you? Which of these is easier to integrate? 3x squared. So you'd make this your dv, you make this u. Okay, so in that case, what's du on dx? Do it together. I mean, that's going to be 3x squared. You've got a 9. That's going to be 27x squared times what? X cubed plus 1 to the power of 8. Okay? I've got my du on dx. I need my v, obviously. We chose it because that was easy to integrate, so you just get x cubed, right? Okay, so let's see what happens when you do this. This integral, I, instead of this, what are we going to end up with? You're going to get uv. There's uv. I'm going to take away the integral of v du, aren't I? Is that right? 27x to the 5? X cubed plus 1 to the 8 dx. Not only have you not solved it, integration by parts is one of the only methods you've got where when you go further in it, sometimes what you end up with is dramatically worse. What's the degree of this thing? That's going to give you 20, degree 29. Yeah, cool. Well, let's expand. Okay, so this is a bad idea. You can see why easy examples, okay, You shouldn't necessarily lead to integration by part.